Okay, well, welcome everyone to this slightly unusual session, which is a mixture of a union session and a great debate, in essence. So we've got 2 hours. We have 2.5 hours. We've got a break of 30 minutes for coffee in the middle. But at the end of this session, we have 30 minutes for a roundtable discussion of the panelists and to open up the floor to you for questions on anything that's been covered by the speakers and material that they've covered. I should say also this is a co-organized session between EGU and AGU, and unfortunately on the program it didn't mention the co-conveners. That's Nick Arndt, who is former chair of our outreach committee, and Eric Davison, who is president of AGU. I'm president of EGU. And I'm going to chair the first half, the first 3 speakers that very, very loosely cover, if you like, the European geoscience landscape and broader research landscape in Europe, and touch on a few things related to funding and the European Commission. And then after the coffee break, very, very loosely, we'll have more of a, if you like, a transatlantic perspective from colleagues who have experience, two actually on both sides of the Atlantic, in Europe and in the US. And at the end, we'll hear from Mike Freilich from NASA. And I'll introduce each speaker, and then we'll have a couple of minutes for any immediate questions related to that speaker's presentation, if you have any burning questions for them. And then if not, we'll move on to the next speaker. And as I said, in the last half hour, we'll have time for plenty of discussion and debate. So you're in for a real treat. We have a really fantastic lineup of 6 speakers stroke panelists here today, covering, I mean, it's almost impossible, it is an impossible task to talk about past achievements and future challenges of geosciences and all aspects of that. And so inevitably, this is going to be a little bit of a selective flavor of things that our particular speakers have identified. First up, we have Catherine Mays, who is Deputy Secretary General of the League of European Research Universities, LERU. Now, you may not be so familiar with LERU. It currently represents 23 universities across Europe. It was established in 2002 with the aim of advancing the understanding and knowledge of decision makers, policy makers, and opinion leaders about the role and activities of research-intensive universities. And it's based in Brussels. So it's an important organization for any of us that are, particularly that work in the higher education sector within Europe. It's basically advocating on our behalf with Brussels. Catherine has worked both in the US and Europe and joined LERU in 2004, covering a range of topics from research funding, doctoral education, and research integrity. And this morning, she's going to discuss European research policy, current outlook, and future perspectives for universities. Yeah, if you want to come up, and you've got 15 minutes on the clock, and then a little bit of time for questions at the end.
Good morning, everybody. I do like this because it's really hard to see the audience with the lights here. It's my pleasure to be here. It's a bit daunting. I am not a geoscientist, and I don't know much about your discipline, but I am impressed by the breadth and the depth of the conference that is going on here. I had a quick look at the program. So without further ado, we only have 15 minutes to start with. Here I go. What am I going to talk about? Basically, a little bit about LERU, what we are, because I think that's important to explain the other things. What is EU research policy? What is the outlook in the near future? And I would say the take-home message there is the stakes are high. I'm going to talk about budget for the next coming years, about things like missions and impact and open science. And I will talk very briefly at the end, if I have time, a little bit about the higher education agenda, because that seems to be making a comeback is my take-home message on that. So I am a linguist by trade, as I said, not a geoscientist, and I thought just to start with I should tell you my linguist joke, because I don't dare to tell a geoscientist joke. I did find this and I thought it was actually quite funny, because it probably relates to me, or I can relate to it. So as the distinguished professor arriving at the campus was looking for the library, he saw a young man and he said, "Excuse me, young man, could you tell me where the library is at?" And the young man goes, "Pardon me, sir, at this institution I was taught not to end my sentence with a preposition." "Oh, excuse me," he says, "could you tell me where the library is at, asshole?" Okay, I hope your jokes are better than mine, but that's my linguist joke for today. So you already know that we are 23 universities in Liru, and we were set up really as a little bit of a mirror image to an American association called the AAU to represent universities in the Brussels bubble, where EU policy making is done for research and higher education. Until we were there were not that many organizations, there were not that many universities speaking up in the European research and higher education agenda. And we are a small group. You can compare us also a little bit to the Russell Group in the UK, if you're familiar with that, or the U15 in Germany, and there are other similar organizations. Indeed, we have ties with all of them. We have once a year also a meeting with all those international networks to talk about EU research and global research policy. So our rectors are our decision-making body. They meet twice a year to set high-level policies and activities for the organization. We are actually based at the University of Leuven, one of our founding members. That's where our office is. We have 7 people, plus the Secretary General himself, Professor Kurt de Ketelaere, there in the front on the left. And, but of course, we find ourselves regularly in Brussels to go and speak to people, etc., etc. These are the actual members of the universities. I will not talk about how they are selected. If you want to ask me that later, feel free, but I'm not going to dwell on that today. As many organizations, we have to show what our impact is, and these are some impact figures of the collective of the 23 universities in terms of gross value added to the economy, in terms of jobs, in terms of what the students that we put out into the economy and the society. There are a lot of topics that we engage on: Horizon 2020 and the next framework program, the budget, open science, the European research area, copyright, NAGOA, dual use, animal research, gender equality, you name it. We probably have a paper, a statement, a policy brief, or at least an opinion about it. We engage in lots of activities. We have about 20 working groups within our organizations, all working on these different files. And we do events in Brussels also. We have a doctoral summer school. As I said, we engage with other universities in Europe and across the world. So lots of things going on. Just to name a few of our recent papers that we have written, one on implicit bias and gender equality, inclusion at universities. We have a paper on interdisciplinarity, on social impact, on excellent education. These are all papers that we published last year. So, a little bit about EU, well, a little bit. This is going to be the main gist of the main brunt of my talk. What is at stake? And I would say the stakes are high, because even though we are secure in Horizon 2020 and the current multi-annual financial framework, which sets the whole budget for the EU until 2020, the talk in Brussels is already very much about what happens post-2020. So it's all about the money. I'll get back to that. I'll talk about missions. What are missions? These are like the new moonshots, or perhaps not. What about impact? The Commission is asking that we have a better approach to impact when we're talking about open science. And these are some of the players in Brussels on this game. Of course, it's the Commissioner for Research, Carlos Moedas, whose strategy for a couple of years now has been to promote open science, open innovation, and to open up to the world. And last year, an influential report was by Pascal Lamy and an expert group, also very important for research policy, with some figures on the budget, which I'll come back to in a minute. Outgoing, or now has left, Director General of DG Research and Innovation is the man on the right there, up there, Robert Jan Smits, who has now, although he's left as director, is going to focus on open access issues. So that's very much something that we're going to watch and interact with as well. And then the woman below is Mariana Mazzucato, a professor at University College London, who delivered a report for the Commission on these missions, which I'm going to talk about. So it's all about the money, but actually it's about much more. What is going to happen in the next year or two is the following. First of all, we are expecting very soon, early May, the proposal for the next multi-annual financial framework. Then in the same month, about 4 weeks later, we're expecting the FP9 proposal, so the successor to Horizon 2020, which is going to run from 21 to 27. Very short timing between those two. That in itself is kind of interesting. Next year, then, we're facing European elections in the spring. Then we'll have a new European Commission coming in towards the end of the year, in the fall. And in the meantime, the presidencies, as you know, rotate every 6 years. We're currently in the Bulgarian presidency. The second half of the year is Austria, then we have Romania, and then Finland. So there's all these things. The Council, the Commission, the Parliament, all have to agree on these, and the timing actually, starting with the multi-annual financial framework, is very short. Our worry is that it's going to be difficult to get everything agreed in place to have an effective start for the 1st of January 2021. So we'll be monitoring this very closely, urging policymakers to go ahead, move ahead. You never can get 100% of what is on your wish list, but compromises will have to be made, and people will need to come to some hard decisions. This whole process is complex. It's a legislative, time-consuming process. Of course, in Europe, there are many other urgencies, whether it's migration, whether it's security, whether it's Brexit. There's a political tightrope here that is going to be need to be walked. In terms of the money, you know, we have about 80 billion right now for the framework program. We and others have asked for a significant increase in that budget. The President Juncker himself, the words that you see at the bottom are by him in a speech a week or two ago, has said that he even dreams about 160 billion. That's in fact also the number that was mentioned in the Lamy report. And he says, je rêve, I am dreaming, but I think we should do it, he says. Je crois que nous devrions le faire. Also, the Budget Commissioner, Oettinger, whose picture you see below that, is very much in support of a significantly increased budget for research and innovation. And of course, that's what we want to go for as well. This will not be simple, as I said, in the times that we are in. Just a week or two ago, we and 12 other university networks in Europe put out this statement, in fact, to ask to double the investment in research and innovation and education to 160 billion. So it's been estimated that this would increase, that this would grow or create an estimated extra 65,000 jobs in Europe and add around 0.46 to GDP. These are the numbers, or these are the types of arguments that you make in Brussels. We all know there are many other things that come into it. I'll get back to that later. But you can read the statement online if you're interested. So, while we need a good program for FP9, last year already we put out a paper which says what should be in that program. And It's about excellence, it's about sustaining the ERC and things like Marie Curie, but it's also about having a good collaborative program. We all know that there are issues with success rates in FP programs, that there are issues with bureaucracy, although the Commission has made headway towards simplification of the program. There's still a lot of things to do. We've also asked for some novelty in that program. It's sort of steady as she goes. There are many good things in it, but you can still improve it. That's sort of the gist of it. So we have asked for things like a different way of evaluation or tweaking the evaluation a little bit, perhaps setting up standing evaluation panels, making sure that real experts evaluate the projects, perhaps impact or what we call follow-up funding for projects that are going somewhere but just need a little bit of extra money to cross a certain border. So what do we know already about FP9? That the 3 pillars are going to be maintained in terms of excellent science, that the second pillar will now be global challenges, that the Commission wants this to be set in the UN Sustainable Development Goals. That innovation is also, that's where a lot of innovation, where a lot of uncertainty is still in it. If you know that there's such a thing as a European Innovation Council, which is now, as a pilot project, has about 2.5 billion. But if you then know that somebody like President Macron comes with a different proposal called JEDI, it's a European Disruption Initiative, which is a, let's say, member state initiative. So you always have that sort of interplay and competition sometimes between what the member states want and what the European Commission wants to advance for research in Europe. There are these tensions. These pillars will be supported by a bottom layer of cross-cutting actions such as the widening and the science with and for society and so on. Defense will somehow be an issue or will be a topic, will be a funded topic in the next framework program, in the next MFF. We don't know yet whether, there's a lot of talk whether it could or should be within the FP9. So, the new kid on the block, missions. This is the idea that, send a man to the moon. We should have more mission-like oriented research in Europe. It's very likely that this will come about in some way of form in that second pillar. The European Commission has already done a consultation on the missions. There were many, many responses, which shows the interest in this issue. What they haven't done yet is select, or they give indications. Lots of topics are being mentioned, but they said they will focus on process first, how to select, how to fund, how to govern these missions. For example, it is said that it would attract top 5 experts to lead a mission. They would pay them market salaries, whatever that means, to be able to get the best people. Now, it's all about what is the granularity of a mission, how specific or how broad do you make it. It could be about future energy batteries, about beating cancer, about zero-emission driving. Those are some of the ones that we turn all the time, but there are many more that are being mentioned. What DG Research also certainly has to do is to look at other DGs, like agriculture. If you think about a mission like pesticide-free agriculture, is how can you really share ideas and money and resources with other DGs to make this happen? The Commissioner, and I realize I'm out of time, if I can have one more minute, has also said next to excellence and openness, impact will be one of the core values of our next framework program. So, but what does impact mean? We have a paper that is forthcoming. I will have to say read it in the next month or so if you want our detailed ideas of how we see that. But what we want especially is for the European Commission not to try and over-engineer impact, and so that scientists don't feel compelled to over-promise what they can deliver. It means that you have to have a sensible understanding and approach to what is an output, what is an outcome, and what is an impact, and what the time frame is in which you can deliver certain things, and then how you measure these things. And the Commission is very much focused on indicators that we can develop for impact. So open science, there the European Commission has 8 ambitions, because it's not only about open access to communications and about open data. It's also about the infrastructure, the so-called science cloud, and how do you measure with new generation metrics. Also, the other 4 ambitions, which are more on the research actors, which is rewards, meaning how do you incentivize, how do you support, how do you promote? It's about actually recruitment, promotion, and retention of researchers that do open science. How do you take that into account in the big picture of careers? It's also about research integrity and about education and about skills. What skills do you need to do open science? And finally, it's also about integrating, or about the link to citizen science. And so all these are for the Commission part of open science. It's clear that this will be a continuing topic in the next framework program. Again, we are coming out with a paper in May, because it will be discussed at the Competitiveness Council at the end of May. Those are the research ministers from the member states gathering, and Moidas will address them with his report there. But there are challenges in this, in terms of privacy, general data protection issues, copyright directive, and so on. So there's lots of challenges there. Finally, just so you know, we're mainly focused on research. Higher education has not been given that much attention. It's funded mostly through the Erasmus Plus program, but again, Macron, I think, was inspirational to the Commission in terms of saying, let's put Europe and its universities on the spotlight. So now it's all about how, in the future, a number of networks of universities in Europe can be formed. The ambitions are high, to have about 20 of these by 2024. How they would exactly, there has been said it should be a geographical balance in there. There could be different types of partnerships. So it's all very much unclear, but what is clear is that something is going to come from this, and something is going to go ahead. It's also related, of course, to recognition of diplomas and something called the EU student card. So in a very short nutshell, these are some of the things that are happening at the EU level in terms of research policy. And since I couldn't say anything about geoscience, I would just like to say, you know, in the end, it's all about the science. And I like these pictures. You probably recognize them as pictures from the March for Science. This is what we are, this is what we do, and this is what we do it for. Thank you very much.
Well, before you dash off, is there an immediate question, anything burning question that anyone wants to ask Katrien? Yes, we have. Can you use the mic? Okay, go on. If you just say who you are as well.
I'm Emma Rochelle, and I work at the French Institut de Recherche pour le Développement. I work in developing countries.
Right.
And so I was really pleased to see that the Sustainable Development Goals are now going to be a central part of the action of the European Union, because there's not much research that's financed in developing countries. And, you know, it's a big problem, and it will become an even bigger problem if we don't support the development of research and higher education in Africa and in Asia.
Yeah.
So I'm really pleased to see that that's part of the new program.
That's yeah. Thank you for that comment. It's an important point to note. Yeah. Okay. Thanks very much, Katrien. That was an amazingly detailed overview of the European research landscape, given the amount of time you had. Next up, we have Professor John Ludden, who is the Chief Executive of the British Geological Survey. He's also past president of EGU and served as Director of Earth Sciences at CNRS in France. His research has been in geochemistry of the solid Earth, and John is going to discuss Earth system science and I think a proposal that he and a consortium of other institutes are developing called Extreme Earth and part of FET, Future Emerging Technology, which is a flagship funding instrument of the European Commission.
Okay, good. Yeah, thanks, Jonathan. Thanks for inviting me. I'm going to do something which I wouldn't normally do, which is kind of pitch a proposal. But it's not just any proposal. It's trying to, I think the Earth and environment or the EGU community need a large mega project which they can get behind. And we've been working on trying to develop one of these future emerging technology flagships. So for those who don't understand that concept, it's essentially the scale of project of the Human Brain Project, the Graphene Project, or Quantum inside Europe at the moment. They're technology-led projects, underpinned by research, but technology-led. And the value of these projects, if you can get them to work, is about €1 billion over 10 years. So it's a significant investment that could come into our community. Now, I think you've also got to put our community into scale after the last presentation, in perspective. Earth and environmental sciences represents around 5% of the total research effort. I mean, we're relatively small, but very important compared to some of the sciences. So in terms of environmental prediction as we go forward, we need more quantitative, reliable environmental prediction is required, right? We're going to need bigger models, we're going to need more resolution, and we're going to need more data to validate and drive these models. And this crosses the entire spectrum from the Earth environment. It impacts on public, it impacts on governments, and it impacts on industry. You're going to see some examples later of big data from space, but we're talking about big data in general and the need to deal with that, and actually the need to deal with that in a computing way. So what happened over the past year or so is that there was a call from the European community for future emerging technology projects. And there were a bunch of them came out, and there were two, in particular in the environmental sector, or in the sort of close to our sort of EGU sector. One of them was called the European Flagship on Extreme Computing and Climate, and the other one was called Ultimate Earth. Now, Ultimate Earth was a fairly sort of Internet of Things of the Earth. It was a fairly soft project. How do you deal with all this massive data that's coming out and becoming available? The flagship program on extreme computing and climate was very hard, very much devoted to how do we develop a high-resolution climate model. So we managed over the past few months actually to bring those two communities together, to bring the extreme computing guys on the climate and the Ultimate Earth people together, which was quite difficult actually. It's very, try and get the solid Earth people to talk to the climate people and say we agree that we have the same sort of approach was very hard, but I think we got there. And we're pitching what we're now calling Extreme Earth. And I'll try and explain to you more or less what Extreme Earth is in a few minutes I have. The aim is, it's one of these future emerging technology projects. It's a big project. It's a big unifying project. It will revolutionize Europe's capability to predict and monitor environmental extremes and their impacts on society. It'll be enabled by the imaginative integration of edge and exascale computing and beyond, and the real-time exploitation of pervasive environmental data. That's the kind of top strap line. Now, I'm going to put my hand up here and say I am not a geophysicist. I am not a data person. I'm a geochemist, actually. But so what I've kind of acted as trying to facilitate some of this process. But the aim is that we can actually take the whole data world to the next level with this future emerging with this FET project. So in particular with a focus on extremes, but not only extremes. If you take some of the extremes that we know of or that we've seen recently, so between 1970 and 2012, severe weather has claimed 150,000 lives and caused total damage of 270 billion. And 2017 ranks as the year with the second highest recorded global reinsurance payouts of 108 billion caused by extreme weather events, earthquakes and volcanoes. And we know that decision makers at all levels are calling for more accurate assessments, more precise predictions on the occurrences and magnitude of these events. Some examples, I'm not going to read them all out, but you can scan those while I talk. Earthquakes, Turkey, the Izmit event killed 17,000 people. Volcanic eruptions, as we know, that Naples is an area of potential eruptions where we need to model it. The Icelandic eruption actually caused enormous disruption, about €1 billion a day, by shutting down air traffic. Droughts and heat waves, the 2003 heat wave affected over 100 million people, over a third of Europe, and cost at least 8.7 billion, with a death toll of 70,000. Fires in Spain and Portugal last year actually claimed 100 casualties and led to an estimated damage of 600 billion. Winter storms and floods. So we know that these extremes exist. We know they're very damaging. We actually know that as a community, we can probably do something about trying to predict them or help decision makers come to some decisions on how to deal with these. So what we've done is we've decided to bring together, this isn't a brilliant diagram, you can probably see most of it. We decided to bring together the climate community, as I said, the weather and climate community, and the solid earth community. And what we said, the climate community challenged the Earth, the solid Earth community, and said, we do high-resolution modeling of the climate. That's what you want to do, step change, where through a concerted effort in harvesting state-of-the-art computing, we can make major changes in the development trajectory of modeling, so we can really improve the modeling. In the solid Earth area, the Earth scientists, or the earthquake people, said, okay, fine. If you want to model the climate at a 1 kilometer resolution, our objective will be to model earthquakes at 10 hertz resolution, okay? Which means sort of a 50 to 100 meters sort of wavelength on shaking. So that's sort of where we're going. We've got two end members of really high resolution modeling, and between those you've got all the knock-on effects on flooding, on infrastructure and such like. And I'll just explain that briefly. So the main objectives are that extreme Earth will enable a step change in the simulation of Earth extremes. And what we have to show with these future emerging technology projects is a step change, a real change in the technology. And it's a technology-led, it's not science-led. Science follows, science comes out of it, but it's really technology-led. So the aim is to develop weather and climate models that are indistinguishable from observations on the 1 kilometer resolution, to create a unified geo-extreme prediction system, forecast the spatial and temporal distribution of earthquake and volcanic processes at regional scale, including fully integrated broadband platform to predict seismic shaking at 10 hertz. Okay, that's all of that step change. To facilitate our ability to fuse observational data from billions of observations, the internet of the environment, call it that, per day into a wholly new view of the Earth system in real time and at full resolution. All right? Really challenging, quite difficult, but it's a future emerging technology is challenging something which is really hard to get to. Linking all these capabilities in simulation of extremes with impacts across the value chain, and actually looking at the impacts and producing full-scale demonstrators for end users. So it's a technology-driven program underpinned by science. And so the technologies that we're trying to bring to the table are, one, as I said before, numerical code acceleration for distributed high-performance computing, which will enable a 1 kilometer horizontal resolution on wall clock day for weather and climate models. Now, you have to ask the climate guys exactly what that means, but you get the feeling for what you can probably do with that. And a 10 hertz high resolution for elastic waves in global Earth models, right? Both of those step changes. Between that, you've got all the data that knocks on from that. Domain-specific big data handling demonstrations of capabilities for high resolution climate, weather, and Earth models, right? And access to manipulate the resulting models through petabyte workflows and simulation. So essentially, be able to manipulate these models real time and change them and model them, right? And to create full-scale end-to-end demonstrations of these models in a cloud-like environment. So I put this up just to sort of make that point. This project is not a capital-intensive project where we're asking for someone to fund the high-performance computing. That sort of activity is happening in parallel with Europe, in parallel inside nations. It's a program where we're asking Europe to fund the algorithms that we will develop to solve the problems, in a sense. And it goes, as you see from this slide, you've got weather extremes, climate extremes, volcanoes and earthquakes, which are the drivers. And then on the other side, environment, health, property. And between that, hydrology, flooding, food agriculture, atmospheric composition, energy and such like. So by doing by taking the climate, high resolution, and the earth at high resolution, the knock-on from that will be a series of applications in areas such as flooding, farming, infrastructure development and such like. That's the dream of this project, that's the aim. So the sort of co-design between science and technology. And essentially, it's a new generation in big data handling, distributed extreme scale computing, and integrated information systems, which develops, at the end of it all, toolkits which go all the way out to the users, right? So this is not being done independently of the users being government, being industry, being the public, right? So it's being done with them. So we think that this is an opportunity for the entire European Earth system modeling and prediction community. And we use the word prediction, right? Even the solid Earth guys are using the word prediction with inverted commas, a difficult one, but we are. Targeting both fluid and solid Earth, it can achieve unprecedented skill levels through a unified and concerted development of transformational information technology. It will create wholly new user communities in areas that have not yet realized the potential of such information. So it's a new generation of users of environmental data that we think this FET Extreme Earth will create. And as I said before, it goes from, this kind of demonstrates the sort of moving forward from it. It starts with these high definition, high resolution models using extreme scale computing, moves out towards sectoral information on things like water, food, energy, health, infrastructure, finally producing tailored service products, right, for applications in the real world. All right? So, one thing that our community needs to do is to think seriously about how we can apply our earth science to the real world and to solving problems. Some of that came up yesterday at the first union session. And this is one way we think we can start to solve problems, and I think I've finished. It's led at the moment, it's led by the European medium-range weather forecasting operation in Reading. They're the leads of the proposal, Peter Bauer. It includes the Max Planck's, NERC, Helmholtz, a series, Météo France, a series of very senior leaders. At the moment, we're just trying to get the momentum behind it, but we also have, you can't read that, but a series of sponsors, and if you can read those, you'll note that several of those sponsors include industry, such as EDF France, Swiss Re, I can think of a few there, et cetera, EUMETSAT. So it's got the main users of this sort of data that we're starting to build this community behind, and essentially that's the message, really, is that I think Extreme Earth, or a project of this scale, is what is required for our community to bring it up to the level of, say, the community behind the medical community with the Human Brain Project, or the materials community with the Graphene Project. And I think Extreme Earth is that platform. I apologize for pitching it, but it's not pitching a regular European project. It's pitching a big dream for the Earth and environmental sciences. Thank you.
Thank you very much. I don't think you should apologize, John, because I think we should all be clear that these FET programs are really transformative. If a project like this is funded, it will support, hundreds, possibly thousands of PhD students, hundreds of postdocs across Europe, and it will change how we do research across a range of fields in geosciences, as John has explained. So I think it's great, actually. It's a little bit different from some of the other talks you'll hear, but this is really, really exciting stuff. So any immediate questions for John on his pitch? Nope. Okay. All right. We'll save them till a little bit later when we have the discussion. I mean, I've certainly got plenty. So the third of our very loosely Euro-focused talks is going to be given by the president of the ERC, Jean-Pierre Bourguignon. He's actually not a geoscientist, he's a mathematician by training and was director of the Institut de Haute Étude Scientifique, IHES, from 1984 till 2013. Jean-Pierre's been intimately involved in European science funding and organisation for many, many years, I guess decades, really. And he's going to discuss the contribution of the ERC to geosciences in its first 10 years. It celebrated its first 10 years, I think, last spring, and is going to discuss the contribution that it may make and preparations for FP9. Jean-Pierre doesn't have any slides. He's going to talk to the audience about some of these points, and we will take it from there.
Thank you very much for giving me this opportunity of speaking about ERC and the contribution of ERC to geosciences. So first of all, maybe just to recall and put my short speech in connection with what Catherine Mace has told you about more broader support by the European Union of research. So really the two key figures which we should always keep in mind when we think about the support given to research by the European Union. Presently, the share of the budget, of the European budget, which you know is really comes from 1% of contribution by countries of their GDP, so it's a small part of their activities. So the share of this budget, the overall budget, which goes to research and innovation is 8%. So that's one first figure. And then the next figure, which is also very important, which is another 8%, which is the share of European funding for the overall funding of research, public and private in Europe. So these are key figures so that you know that the share which comes from European sources is not major, it's actually secondary. But we hope it's still transformational, so that's the whole point. That is, and then, as you know, it has been a long struggle by the scientific community to obtain that really research be funded as such by the European Commission, which was not the case for a long time for really legal reasons, which was that research was not a shared responsibility, and it was changed over time, and really typically by the Lisbon Treaty 2009, but already earlier some possibility were done. Before, the only way research could be funded was because it contributed to European cohesion, therefore the support to networks, or through wealth creation, therefore the importance given to projects which involve industry at the same time as academia. But now these times are over, and this allowed the creation of the European Research Council, which the scientific community really struggled for more than 10 years, in 2007. So last year we celebrated 10 years of ERC. It was a great opportunity to look back, but also to think about the future. So now, concerning ERC, the present situation is the following one. So we are funded over the period 2014-2020, which is the present framework program, 7 years, which is called Horizon 2020. So we represent 17% of this budget. And Catherine told us it's usually mentioned to be 80 billion. It's slightly less because some was taken away, so it's more like 75 billion. And so it's ERC is receiving for this 7-year period a budget of about 13 billion. That's the amount of money which we have at our disposal, which was flat at the beginning. So for the year 2014, 2015, 2016 at 1.6 billion. And we passed the 2 billion mark last year for the first time. So for the first time last year, we could fund in a given year more than 1,000 projects. So the whole purpose of ERC has been to fund projects submitted by individuals, of course with the purpose of funding a group around them. The group can be small, can be larger, it's totally left to them, in a strict bottom-up approach. So this is the philosophy of ERC. People propose what they consider is the most challenging, the most interesting thing they want to develop. There is no priority on anything. and we organized the domains of knowledge in 25 panels. And one of them is really most directly relevant for your community, which is the panel called PE10, PE for Physical Sciences and Engineering, which is called Earth System Science. So this is the one which has been funding the largest number of projects in your domain, but also some others have been funding in life sciences, some which have to do with ecology, which also are relevant for your community. And actually there are a number of other panels which have been also considering projects connected to really geoscience. So this is what we are. So what did we fund in these 10 years, or almost 11 years now, in geosciences? Typically, we funded 300 projects, actually exactly 305, and these projects represent almost 600 million. So it's a very significant number. And if you look at the people who were funded with this, that is thanks to this money, you had doctoral students, postdocs, and so on, it's about 8,000 people who have been funded. So it's a significant share. And these projects really cover many, many different areas. And so I leave it to somebody who knows the domain much better, Barbara Romanovich, who is a member of the Scientific Council of the ERC, who will tell you more about really an inside view from the ERC concerning geosciences. My point here is more to talk about the general impact and how much has been done. But another figure which I want to bring up, because it's one of the key elements of our strategy to get our budget increased for the next framework program. So Catherine already told you the next framework program will be 2021 to 2027, so again 7 years. There were discussions to make it 5 or 7 or 10 years. Finally, 7 has prevailed. And one of the key arguments, I will give you another one in a minute, was really to consider how many projects have been considered by the panels as absolutely excellent, should be funded, but actually we could not fund them because we don't have enough money. And in the geosciences, the number of projects which we felt were all through, which meant excellent and really should be funded, is exactly in these 10 years 150. That is half the number which we funded. So we feel that definitely, because our success rate presently, and the success rate of geosciences also, which is exactly the average, is 12%, which is the present success rate. So for the request for the next budget for FP9, the next framework program, we defend the idea that the success rate would really get up to 15%. And if things continue to be the way they are at this moment, it looks like we can definitely we will not decrease the quality, which is of course something people are very keen to know, whether there is room for more money without affecting the quality of the people funded. So this is one good reason to ask for more money for ERC. Actually, in its statement released last May, by the European Research Council, Scientific Council, to really our position for the next framework program, we had 3 keywords. The first one was continuity. That is, by this we meant that we felt the present structure was viable and we should be able to continue with this present structure, which gives a lot of power to the Scientific Council, who are fully responsible for how we spend the money and who is evaluating the projects, which is of course key. The second keyword was agility, because we felt that some things we are doing at the moment painfully should be very simple. And so we asked for a number of new possible activities for the agency supporting the ERC. And the last but not least, of course, is something I already mentioned, which is scale up, which is what should be the budget for ERC in the next framework program. And for this, we really asked for, again, a doubling of the budget of ERC, with the perspective that the budget could be 4 billion in 2027. As I told you, for this year, for the first time, we passed the 2 billion mark, which is a very significant amount of money. But the second element I want to bring up, because it is already something which is available, which I think is relevant for your community, is the decision by the Scientific Council, which was tough on the agency, to relaunch already in 2018 a program which existed 2 years in 2012-2013, which is called Synergy. As I told you, I mean, the whole principle of ERC was to support projects submitted by researchers, typically one researcher. But with Synergy, we open up the possibility that people who present a project could be a group of up to 4 people. That is 2, 3, or 4. And of course, on top of these research scientific quality as being, of course, the main criteria, the people will have to prove that there is a real synergy between them. That is really, it makes sense for the problem they want to attack, that they join forces because they are typically coming from different communities, and this pluridisciplinary dimension is, we hope, for synergy will be one of the key elements. So we, as I said, we relaunched this for 2018. The closure for submitting proposal was the 15th of November last year, and we received exactly 300 proposals, which was actually exactly the target we had. Why did we think this target was a good one? Well, first of all, it was significant enough to test the new evaluation scheme process that we have put in place, which is a 3-step evaluation, which we hope is going to be very adapted to Synergy. But second of all, that it was not so big that, again, the success rate would be ridiculous, as it was in 2012 and 2013, where the success rate was typically 2%, which doesn't make sense if you look at how much effort goes into preparing the proposal, how many people are funded. So this time, the success rate should be around 10%. We put on the table for 2018, 250 million. And for 2019, which of course the call is going to be open during 2018, the amount of money we reserved in the work program, which is not yet published, but will be published by July, is 400 million. So we expect a larger number of applications for the coming year. So for us, Synergy, just to give you a quick idea, so we, as I said, we received 300 proposals, and typically they, in average, have 3.5 scientists in these groups. So most of them are indeed 4 people working together. Most of them are more senior scientists. And I wanted to end with this, which is the effort and decision by the Scientific Council from the very beginning to favor younger people in the normal competition. That is 2/3 of the grants we give, or also more or less 2/3 of the money we give, is indeed for younger people. So 2/3 of the people we fund are below 40 years of age. So in a sense, ERC has been funding. So far we have funded about 8,000 grantees, ERC grantees, and typically we have almost 6,000 of them who are actually under 40 years of age. So it means that the contribution of ERC to the constitution development support of the next generation is very considerable. So these were the messages I want to tell you, and my final word is to say, if we are going to win this battle to get the next budget for FP9, really grow as we need it to grow, we consider 120 billion as the really bottom line. We hope it could be even better, because you have to think that this budget is a priori without the UK. We hope the UK is going to join as an associated country, but that's a decision to be made, and of course negotiation on the way. So it will mean that the contribution by UK will be added to this, because they will have to pay cash what they for the moment get automatically because they are members of the European Union. So this is where we are. So I think the contribution of the European Research Council to Geosciences has been significant. I hope you feel so. And at least we know this community is extremely well organized, extremely thriving, and you've heard a very global project, a very different nature from ERC. ERC want to encourage individual initiative, but we know that to develop any individual initiative, you need to be in the right community, you need to be supported, you need to be in a good environment. Thank you very much.
Thanks very much, Jean-Pierre. Do we have any immediate questions for Jean-Pierre on ERC funding or anything that he talked about? I mean, I actually, a real quick one, Jean-Pierre. We have a couple of minutes. So I think Jean-Pierre mentioned synergy grants. So these are somewhat bigger, significantly bigger than regular or regular inverted commas ERC grants, which have a budget of about 2.5 million. You used to have, you had these for a short while, they disappeared, and now you've reintroduced them. I wondered what the thinking behind that was, and I think, the other thing is that synergy grants actually are a really valuable funding route for geosciences, which is very interdisciplinary and where you can't tackle a problem from one institute alone, say.
So the first comment is, what is the amount? The amount of money which is possibly put at the disposal of a group is up to 10 million for 6 years, but it can go up to 14 million for 6 years if people have special needs for equipment or access to large facilities. Now, why did we stop in 2013? Actually, the budget for 2013 for ERC was 1.7 billion. And as you heard, the amount of money which went into synergy was 150 million with a ridiculous number of projects funded. The first year, there were more than 700 applicants for 11 projects funded. Second year, more than 400 applicants for 13 projects funded. Right. So the success rate was ridiculous. So we felt it was unreasonable to continue without having a check. Actually, within the Scientific Council, there were different opinions. There were some people who were very supportive of synergy and people who were very critical of synergy. So we set up a task force to look to that. And this task force visited all the 24, 11 plus 13 synergy projects to check whether they were really different, how they were working, and so on. It was early in the process, so they were not yet finishing. But it was interesting that this task force, half the people were for, half for against. After this visit, they were all for. Right. So now we looked at, now to answer very precisely your question, we looked at the possibility for really when we could relaunch this. So we had to wait until our budget was large enough. As I told you, we started 2014, 2015, 2016 with 1.6 billion. That is 100 million below what we had in 2013. So there was no room for really synergy. So the first year we thought there was enough room for synergy was in 2018. That's what that is this year, where we could put on the table 250 million. And because our budget continues to grow until 2020, that's why we feel that we can put for 2019 400 million on the table, which we hope will still make synergy competition with a success rate similar to the other one, which is typically 10%, which I know is so big, but it's not the ridiculous 2% which we had in the beginning. So that was the reason for waiting and relaunching, but also checking very thoroughly the evaluation scheme.
And the four partners, the four main partners, they have to be within the European Union to receive the funding. But is it possible to have international partners that are funded?
That's the situation. So for all ERC projects, you can always have collaborators under your responsibility. You're outside. And so we do fund research which is done outside Europe, provided it is, of course, presented during the submission and that you justify it for the purpose of your project. Actually, we are considering, and it's part of the work program to be approved for next year, that maybe one of the four could be somebody who could be elsewhere. Yep. And of course, still the same applies, namely that person will have to be part of the team and the people have to prove that indeed there is a synergy between them and that the collaboration of this extra person makes a difference for the success of the project. So
maybe we'll come back to that later, but I think that's a really important point because from my own experience, it's extremely difficult to fund genuinely international projects with partners from outside of the EU or particularly from the US. So
that was our motivation.
Yeah, exactly right.
But as you know, it's some people feel that since this is taxpayers' money from Europe, then there is an issue there. Thank you very much.
It has to stay right here. Yeah. Okay, I'd like to thank the first three speakers. And just remind you that after the coffee break, we have three more with more of a sort of transatlantic view of geoscience research. So I look forward to seeing you in half an hour.
Welcome back. My name is Eric Davidson. I'm the president of the American Geophysical Union, and I want to thank Jonathan Bamber for organizing this co-sponsored session of EGU and AGU, and it's my honor to be able to introduce the next three speakers. And as Jonathan has explained this morning, this group all has in common some transatlantic experience, and so that's the theme that we've organized for the second half. Our first speaker is Barbara Romanowitz. She's a seismologist, and she shares her time between the Collège de France and the University of California at Berkeley. She's a member of the Scientific Council of ERC. Her research focuses on developing seismological imaging techniques for application to the deep earth. She'll be discussing the challenges related to seismic tomography in maintaining long-term high-quality data acquisition and archival for the research community, and the need for instrumenting the ocean floor. Barbara.
Good morning. Thank you for giving me this opportunity to present some of my views. What I said I would present is a little different from what I'm actually going to present. However, in such a short time, I had to make some choices, and so as a global seismologist interested in deep earth, you will find some biases in what I have to say, but hopefully also some general thoughts. How do I use this? Just click. Okay, so there are basically three areas in which I would like to kind of point out, as we have made a lot of progress in, and I think this applies not only to seismology, but all the disciplines involved in deep earth interior research, is in the last 30 years a tremendous progress in the quantity and quality of data that are available to us. This is true of seismic data, but it's also true of geodetic, mineral physics, geochemistry, you name it. Associated with this, of course, increases in computing and archival power, which have been extremely helpful, and it's only the beginning. And then the third element, or the third leg, is associated with this, the development of new computational and analysis tools. So I'll give some example just from seismology. The Federation of Digital Seismic Networks is an organization which combines contributions from many countries in the world to install and acquire high-quality broadband data from seismic stations useful for studies of earthquakes as well as deep structure. You see it's been in existence in 30 years, but I wanted to point out the kind of vision that was involved in this at the beginning and which has carried on and has been very fruitful. The standardization of the broadband instrumentation and of the data formats that has allowed much easier data exchange and utilization today in the context of big data. The fact that the data have been acquired in continuously, which I will illustrate in a minute, has had important implications for the science. And finally, the fact that the data archives that are associated with this are open data. And you see this network, this is just a small portion of all the seismic broadband stations that are in the world, just to give an illustration, however, of the international cooperation that is involved in these developments. So, so there's a global network, but in recent years it has been augmented by efforts to densify the station distributions in some regions, which is of course important as we strive to improve resolution in our modeling. So I want to cite the US array, which covered the territory of the US plus Alaska in the last 10 years with broadband station every 70 kilometers. And another example here in Europe is that of Alperae, which is currently in its being developed with collaborations of many countries in Europe. These, as I mentioned, an important aspect has been the collection of continuous data, and in fact it has resulted in a completely new field in the last 15 years, which is that of ANT, seismic ambient noise tomography, which was first proposed in the 1960s, that you could extract information on the effects of structure on the propagation of waves by taking cross-correlation of noise records or continuous noise records between two stations. And here is an example of some early papers showing how you can extract the surface wave propagating from one station to another from, basically combining the records from many years of data in the absence of earthquakes. So that has allowed, that wouldn't have been possible without continuous recording, and that has allowed this new field to get into basically free ourselves from necessarily waiting for earthquakes to study structure. Now this is, of course, very important for the study of crustal structure. Here are some examples, older and newer, because these signals are the strongest in the area where the noise is the strongest, the so-called microseismic band, which provides information on shallow structure. But in recent times, there's also some progress in extracting information on really deep structures all the way to the inner core of the Earth. The availability, so this is the availability of data, continuous data. The availability of computational power and new computational techniques has allowed the development, still ongoing development, of what's called full waveform tomography, where now you can compare a whole seismogram, so the whole information from an earthquake, with a accurately computed synthetic, predicted seismogram from a given Earth model, and use this to improve the Earth model. Previously, most of imaging studies relied on only small portions of these seismograms, and now we are getting to the point where we can utilize the whole information in the seismograms. And this is made possible by being able to compute the wave field, the seismic wave field, in 3D models of arbitrary complexity using numerical methods. Quite challenging computationally, but now accessible. And so some of the results, necessarily biased, we are now in a position to really be confident that there are mantle plumes. This is a model using standard techniques where you can see something that looks like plumes across the Pacific here. This is cross sections from the core mantle boundary to the surface. But if you're a skeptic, you will say, well, there's other, red blobs, red meaning low velocity, meaning hotter than average, kind of like a plume near these volcanoes, these hotspot volcanoes in the Pacific, Pitcairn and McDonald. But with the new techniques, these images become much clearer. And at the global scale, we have still some progress to make to improve the resolution of these big structures. And, if you look here, you see some big structure. There is the question of the Yellowstone hotspot and whether it is associated with a plume. This is from the same model, but now with the US array and the densification of stations, we are also starting to see clearer pictures of what goes on below this structure. And so there may be different kinds of mantle plumes, some big ones and some small ones that may be thermal or maybe thermochemical, things that need to be assessed in the future. Now, global seismology and plumes, but also regional seismology using numerical methods, increasing the resolution. And here the point is to say that we're getting closer and closer in terms of techniques and ways of imaging with the area of exploration geophysics. So this is also a new development that these two communities are becoming much closer together thanks to the development of techniques, numerical wave field techniques, and also the density of data. So I want to then move on to challenges. The challenge in terms of data acquisition that I have chosen, which I think is really our highest priority, is the need for broadband stations in the oceans. If you remember the map showing the distribution of stations, incomplete map, but still an idea, you will see easily that the oceans are not covered, and so or not sufficiently covered, and so it is quite a problem for improving resolutions of structures, from addressing issues such as even the underlying kind of dynamics of plate tectonics in ocean basins, and all the way to improving resolutions at the global scale. This is just to show that this is a problem that has been around for a long time. In fact, I became involved in trying to put stations in the oceans already 30 years ago, and there was an international effort to to kind of make progress on this by basically collaborating on the international scale, which was established in the early 90s. And this is just to show, as I was preparing this, a little bit of history. The idea was at that time, to install permanent observational stations on the ocean floor, in particular by drilling holes in some critical areas that were not covered by stations. And so in the context of the IODP, the International Ocean Drilling Program, several holes were drilled, one in particular here in the Pacific, another one in the Indian Ocean, with the idea that these would be sites for permanent seismic stations. Unfortunately, this never happened. There were efforts that did happen. Okay, so this is just some chronology. There were efforts that did happen, just some examples: broadband stations near the coasts, cabled observatories in various areas of the world, and this is not an exhaustive kind of list, but nothing really to study the middle of the ocean basins. And in recent times, very recently, this has come up again, and with new initiatives, new ideas. And now we are switching from the idea of permanent observatory, which is extremely expensive, extremely difficult to realize technologically, to something more in the concept of those broadband arrays like US Array or ALP arrays, so installation of stations in small arrays, but for a sufficient amount of time to collect enough data. And so this specific array concept, this is my view, my preferred view, a broader, larger apertures array, but of course more difficult technically and financially. And some of these are actually coming to life. There is one project, HAXB, which is a US-funded project, which is currently, they're going to sea as we speak. And then another one, a Japanese one, oldest, which I am told will start in this fall, the fall of 2018. So some progress in this direction, but still a long way to go. So now for the rest of the speech, I would like to sort of expand a little bit beyond just seismology and talk about broader challenges that our community faces in general. There are many fundamental processes that we still don't understand about the evolution and dynamics of our planet. And this year we are celebrating the 50 years anniversary of the acceptance of plate tectonics, and we still don't really know what are the forces that drive plate motions in any detail. We don't understand how new plate boundaries are initiated or when plate tectonics began, and why is the Earth alone with plate tectonics among the terrestrial planets in our solar system. And to solve this, we cannot none of us in our own disciplines can really solve the problem by ourselves. We are really a multidisciplinary community, and we need the contributions of the seismologists, the geochemists, the mineral physicists, the geodynamicists, etc., to really provide the constraints, which are only partial from each discipline, to understand the Earth's internal structure, dynamics, and evolution, and of course grounded on observations both at the Earth's surface and remote sensing using satellites. So this is a cliche, but this is really what it is. What we face in our discipline is that we all have a little piece of the puzzle, and we need to bring all these pieces together to really advance. And now, how can we do this? We really need to have a concerted effort across the disciplines, and the synergies across disciplines are really challenging. They're not easily come about because each of us has our own specialty. We're very competent in our own specialty, but we don't necessarily understand very well at the technical level the complexity of other disciplines. So these are new demands on researchers that have become very specialized. And also, so in particular, there is a need for education of geoscientists at all career levels to think in this multidisciplinary way. And I will just give two examples, one in Europe of efforts going in this direction, on different aspects. One is EPOS, the European Plate Observing System, which is a European initiative, and then the CIDER, the Cooperative Institute for Dynamic Earth Research, in which I have been involved myself, and which is at the present led by US, funded by the National Science Foundation. So what is EPOS? EPOS is an effort to integrate the research infrastructures for solid earth science in Europe. It basically takes what already exists, the facilities that already exist, and tries to put it in a common framework to have a common kind of hub, so that there is a sort of single distributed infrastructure that takes advantage of current technological abilities. And it currently is in a sort of development stage, involves 25 countries and about double participant institutions, and is aimed at collecting all the data from all possible existing seismic stations, GPS stations, you name it, and also, interestingly, even data from laboratory data, for example, models, geodynamic models that are constructed either from numerically or in the laboratory, to share the results, to share the parameters and other details of how things are done. And so right now it's in its implementation phase, and the goal is this year for it to become a legal entity. Now, finally, CIDER is a different kind. It's more of an education kind of program, and basically the goal is to improve the effective communication and understanding between the different disciplines, that provide an intellectual framework for multidisciplinary research in the geosciences, so that we can tackle these fundamental questions that we cannot answer each on our own. It provides the necessary complement to growing infrastructure for the data gathering and distribution, which has been growing tremendously. Whoops, what's going on? Oh, I'm going in the wrong direction. So very briefly, CIDER was inspired by institutes in other physical sciences that foster informal interactions. The real kind of main inspiration came from the Kavli Institute of Theoretical Physics, but it had to be adapted to the needs of the earth science community, and particularly because we have a very significant experiment and field component to our work. So we don't just need a pencil and paper to be able to kind of relocate and work together for a long time in a particular location. There was a community workshop which provided broad support for the concept, and then following up community workshops as it was developing. And basically one of the core aspects of this is a summer program, which is alternatively held at KITP in Santa Barbara or at UC Berkeley. And what is special about these summer programs, which are always on a different theme, is that it is a long program. It involves lectures and tutorials for students across the disciplines that have to spend 4 weeks on site, and the senior participants, lecturers or other, have to spend at least 2 weeks in the program. So this creates an opportunity to foster exchanges at a much deeper level than you can do in regular workshops or conferences. This is just some examples of the students. And what are products? The products are, first of all, a cohort of students that represent different disciplines and that then go on and continue to communicate with each other to help each other out throughout their careers. The collaborations lead to publications and proposals. And in particular, and as I mentioned, networking among participants is very important. So I guess to finish, I just wanted to make a pitch that I think this kind of program also needs a component in Europe. CIDR is funded by NSF and can bring in only a couple of participants every year from Europe and Asia. But of course, science is international, and it would really be important in the future that some similar program, or in coordination maybe with CIDR, exists in Europe. And thank you very much. I think.
Thank you. Perhaps we could take one quick question, if there's one. Okay, thank you very much, Paul. Well, that was a wonderful review of challenges facing solid Earth, deep Earth processes. About a couple decades ago, both the American Geophysical Union and the European Geosciences Union and others around the world recognized and embraced including biological processes at or near the Earth's surface. And the biogeosciences sections were born. And today we have the pleasure of having Susan Trumbore, who is one of the founders of the biogeosciences section of the American Geophysical Union. She currently directs the Department of Biogeochemical Processes at the Max Planck Institute for Biogeochemistry at Jena, and also continues with her appointment as Professor of Earth System Science at the University of California. She's been studying radiocarbon as a tool for studying the dynamics of carbon cycling in terrestrial ecosystems. And she'll be discussing the dramatic growth of the biogeosciences within the discipline over the past 2 decades and the need to include the role of biota in many of the grand challenges in geosciences. Susan.
Okay, thanks, Eric. So it was very difficult to think about what to put in a talk like this. So I'm going to spend a little bit of time about the past and also to congratulate, I think, the societies. The Earth Sciences is one of the few disciplines that's welcoming to expanding, and one of our challenges is how far to go, I think, with that. So if you look up biogeoscience in the Merriam-Webster dictionary, you get a very helpful thing. It's the interdisciplinary studies that bring together the biosciences and the geosciences. But I think, we all kind of know more or less what we think that is, but I think one of the trends in the history of science was, in the late 1800s and early 1900s, there was kind of this natural science idea that both biology and geology were not necessarily so separable. I've got a quote here from Arthur Tansley, who's one of the early ecosystem scientists, that says, even though we might want to study organisms or we're biologists, we can't fundamentally separate them from their special environment with which they form one physical system. And so as in the mid-century, I would say, the things got stovepiped, biologists were trained separately, largely from geologists, and towards the end of the last century, those things started to come together again. Of course, biota interact with their environment. They largely do that through the actions in the atmosphere and hydrosphere, as well as the surface part of the geosphere. So let's see. Do that. So to me, the biogeochemistry is really the study of the Earth's metabolism. We can go back again to the early part of the last century with Vernadsky's introduction of global biogeochemical cycles, the first study of that. But then you can also take it to the reemergence of some of these ideas, taken maybe to an extreme by James Lovelock's Gaia hypothesis, that putting all the organisms on Earth together, they can function somehow to create a homeostasis, and really focusing more on the feedbacks between the Earth physical system and the biological systems. And if you want a nice history of all that, you can read Evel Gorham's paper on the origins of biogeochemistry, which is I really enjoyed. So an example of what I'm trying to talk about is, I'm old enough to say when I was a graduate student back before the internet, we learned about the Redfield ratio in our chemical oceanography class. And the Redfield ratio is this idea of a fundamental ratio of 106 carbon atoms to 16 nitrogen atoms to every phosphorus, and that this was sort of the canonical organism that lived in the oceans, and that imprint of that organism could be seen in the inorganic distribution of inorganic carbon, nitrate, and phosphate across all ocean basins. So my PhD advisor, who's a very famous chemical oceanographer, said, what do I need biology for? I have the Redfield ratio. And I think a lot of us also felt that way. We have the law of microbial infallibility that, if you can get energy out of it, a microbe will do so as fast as it can. And I think what's changed is that the closer we started to, as more and more data came out, this 16-to-1 line for nitrate to phosphate in the oceans doesn't always exactly fall on that line. And although we learned a lot about marine biogeochemistry from the observation of the Redfield ratio, it was that understanding what those deviations mean, and here it's nitrification and denitrification are brought in as the processes that do that. But if we want to understand how the ocean might have been in times that were not exactly like our own, maybe when nutrient supplies were different, and how variable this ratio might be in time, then we need to understand the underlying biology. So now the Redfield ratio, you might call it an emergent property that includes many the ecological communities of the ocean, none of which have exactly the Redfield ratio, but working together, they somehow give us this number. And I think that's what's happened with bringing biological understanding more into geosciences. And so it was really those kinds of observations that led biogeosciences to be formed, because the scientists themselves recognized the need to understand and better integrate the key role played by biology into a lot of the things that we wanted to understand about the Earth and other planets and the potential for life to be present on other planets. So I'm most familiar with the AGU. So it was actually a bottom-up thing there where people said we need a new section in AGU, which was something that hadn't happened before, or hadn't happened very recently. And enough people got together that it was done. And the first year, 2001, when you could affiliate, there was about 3% of the AGU membership then, which was about 1,000 people. Now there are 14,000 people who claim an affiliation. And if you go to the AGU annual meeting, something like 10% of the abstracts are in a biogeochemical heading. The same as here, very similar history in EGU. I'm not as familiar with it, so maybe other people can comment, but it started, the first time I can find records are in 2002. I know there were people active before then. By 2017, the meeting had about 11% of the abstracts, and I think this meeting is, I'm sure, very similar. So it's not dominating the societies, but it's definitely not something we can ignore. And I think we can't ignore it because the scientific topics that are bringing new people into the geological or geophysical unions, geoscience unions, are people like ecosystem ecologists, geomicrobiologists, who come to this meeting and realize that they have to understand something about how nutrients are delivered, how oceans circulate or how the atmosphere circulates to really understand the behavior of organisms in their environment and how they interact. So these are just a list of some of the important questions, and they line up very well with some of the Sustainable Development Goals which is good, and I think is one of the reasons this has been an expanding field. So the coevolution, the fact that the biosphere is the main source of sink of most of the important gases we want to study in the atmosphere, whether we're studying climate change, long-term evolution of the life and the atmospheric composition, and especially for understanding greenhouse gases over time. About the time that this was becoming important was actually a lot of it was with the fate of acidic precipitation on ecosystems, understanding the impacts, but also the fates of something like the nitrate and nitric acid. The recognition of the importance of living in organisms in the distribution of where we can find mineral deposits on the planet, and also the understanding that we can't predict. One of the reasons we couldn't predict the kinetics of things like weathering reactions was because there was biology involved. And finally, the discoveries of, one of the things that inspired me to go to geology in college was the discovery of black smoker vents, which were, these extreme environments that nobody knew existed, and, now, they have a biota that functions in the absence of most of what we think is important, like sunlight. So, and all of that, I think, leads to how we might look for imprints, biosignatures, that we can interpret in the many, many terrestrial planets that are now being discovered. So biogeosciences has obviously grown. I think it's brought new people and new disciplines to the earth science community. It's also brought these pretty successful journals from both societies, the Biogeosciences and JGR Biogeosciences. When I was president of the Biogeosciences, we actually were in negotiation with our partners in the EGU to try to make one journal from both societies, but the different publication policies didn't allow us to do that, but can dream. So that's just a little bit of the history, and I wanted to, like others, talk about a few challenges, and I'm going to echo much of what you've heard already about data and everything else. But I feel like, in this last period when biogeosciences has become into these societies, there's been this revolution in the omics revolution in biology, which makes me glad that I didn't learn biology when I was in college, because it would be totally useless now, whatever I would have learned then. So this idea that you can go from genes to, you know, the transcriptome, to the proteome, to the metabolites, where, you know, you're starting to be able to understand the chemical diversity of living organisms and document it, and even from this chain, how those molecules get made. So this is a lot of the field of chemical ecology, you know, linking the evolution of metabolism. You know, if you have a different metabolome, what does it mean for the differences in genes, and when things evolved to change the chemical imprint of life. But what is very clear from all of that, the big challenge is, what does that mean? We can document that, you know, instead of, you know, dissolved organic carbon, we can now say what molecules are there, but we still don't understand what their purpose is and why there are so many of them. So I think that's one of the really big challenges from the biological side, which involves big data, collaboration, and everything else. The other question, and the next speaker will talk about the data from observing the whole Earth, which is, I think, the other big challenge, and the big revolution. You know, we've only had satellites for about, since the 1970s, you know, giving us a picture of the Earth's surface, and now we're getting a lot of information that can be combined in different ways. But how do we go between those scales? So, you know, if we think about something like a question like, why did the amplitude of the seasonal cycle of CO2 increase at high latitudes over the last 50 years where we've had observations? Well, obviously that has something to do with photosynthesis and respiration, because that's what's controlling the seasonal cycle. Ultimately, that has to do with the Rubisco enzyme and how it functions. But what's the most important thing in this chain? If we're looking at the extreme Earth proposal, which is, you know, we want 1 kilometer resolution for our climate data, is that going to help us with that particular question? Or do we need to include other processes? And I think we're still struggling with both spatial and temporal scaling. What are the processes that really influence the next level up? And do we have to understand how Rubisco works to make this chain go? So, you know, the omics revolution is at the very small scale, very detailed, but how much is that really going to help us at the large scale when we want to understand global change? And I think that's a huge challenge for our community, which, you know, we need models to go from every scale to the next one. So some associated challenges, you know, one of the reasons, you know, we are not very good at predicting, say, carbon storage on land into the future is because we really don't understand how organisms and ecosystems adapt to change. And, you know, we can't just maybe use a Q10 to say what's going to happen into the future. And I think there's a really big question, especially in modeling the role of plants and ecosystems at the global scale, as to how much biodiversity matters. And there are also, not just for the biogeochemical side, there's also the physical climate side of the question, how much, you know, how do, is cloud cover, how's the radiation balance of the Earth, and the water budget impacted by the fact that there's land vegetation. Other questions that I'm not as expert at, you know, we now know that most of the biosphere is not this little thin skin at the surface of the Earth that includes us. It's the microbiome that extends quite deep, and we don't really understand what it does there and how it evolved. And that all, again, goes back to this question of how does life originate, and can life exist on other planets in forms that we can't think about? So another challenge, I think, is that we have to think how far we want to expand our disciplines. So whether we agree or not, we're now living in a time when people and their behavior really are one of the big geophysical forces, maybe not for understanding deep Earth dynamics, but for understanding a lot of what happens at the surface. And I think, if we look at climate models going into the future, we can talk about uncertainties, but by far the biggest uncertainty in what the temperature is going to be in 2100 is not whether the models are getting details right. It's what we drive the models with, what people are going to do, whether we're going to stop burning fossil fuels or keep going. And we don't study people. So that's one of the questions, how much to bring the next step into our societies. I mean, there are clearly many, many sessions here that include, human behavior and attempts to bring those sciences in. And I think that's one of our big challenges, at least in the global change community, because we're not studying the biggest driver in a way that we can predict it. And then finally, I want to echo everything that was said about the challenges of maintaining observations, especially long-term. I heard a great talk yesterday about, there are a lot of these non-sexy, really basic measurements that we don't often get funded to go out and measure. In soil science that I'm familiar with, it's bulk density, it's the volume. If you take a volume of soil, how much of the mass of solid and liquid is in there, and so I can calculate how much pore space is there. It's not a very sexy measurement. You can't sense it from space. You have to go out there and take a piece of soil back to the lab and dry it out. But it is the fundamental measurement that's needed to change what's happening in my little sample to try to extrapolate it larger. So I think we really need to think about what are these, non-sexy things, and how do we get, like as the seismology community has done, how do we span and calibrate ourselves so that we're all making the same measurement and can link across many biomes and other things. So the model of that has been this National Ecological Observation Network in the US, where a lot of the observations have been outsourced to professionals who provide, measurements that are made the same way across different biomes in the United States. And that's an experiment in how to do that kind of science, taking it away from the individual investigator and saying, no, we need a professional, we'll provide the data, you tell us, you use it to answer your questions. So I think there's other things here about maintaining and supplementing autonomous sensors in times of restrained budgets. And then finally, I think we face as a society, because I haven't heard this from anybody else, I'll go a little over and talk about demographic challenges. I mean, we hear a lot about gender and geography. The gender part, the biogeosciences tends to be younger and more female than the average AGU member. I'm not so sure about EGU. So we're more looking at the future. The field should grow. But I think we really do have to ask a question I heard earlier about how can we support scientific endeavor at the global scale, not just European and North American investments. And I think that's all I had to say.
Thank you.
Thank you.
I forgot to mention when I introduced Sue that when I first met her, she introduced herself as a soil oceanographer. And I think you can see why. A few quick questions for Sue. Okay, great. Thank you very much, Sue. Well, at AGU, we often refer to our science as the geosciences, but also sometimes we refer to it as the earth and space science. And so that includes space science, the study of space, but also the study of Earth from space. And so our final speaker is Mike Frelich. He's a space oceanographer, right? Who, for the past 11 years, has directed NASA's Earth Science Division. He's led all of NASA's Earth-focused flight mission, research, applications, and technology development activities. He's had leadership positions in many interagency and international coordinating groups related to Earth observation, and seeks to apply knowledge and the unique measurements from satellites to provide benefits to all humans. He'll be discussing satellites and science in service to society, accomplishments and challenges. Mike.
Well, thanks very much. For several decades, I was on the faculty at Oregon State University and eventually became associate dean. And I was called the Dean of Space Research. People needed space for labs. And so, and interestingly enough, in the early days of observing the oceans from the vantage point of space, people talked about space oceanography, and I fought against that dramatically because nobody calls themselves a ship oceanographer. Soil oceanographers never entered my mind. So this talk actually, although we were uncoordinated, I think maybe we were all twins separated at birth, fits in, I think, fairly nicely. We've heard about, starting with John's talk, we heard about Earth system science. Susan and Barbara talked a lot about the complexity and interdisciplinary nature of understanding our planet. Our planet is a complex system for sure. There are processes that are occurring on the land, in the atmosphere, in the ocean, in the solid earth under the surface, chemical processes, biological processes, thermodynamic, dynamic, and human processes as well. To understand our planet as an integrated system, we have to understand not only individual processes, but the connections between them. And I maintain that the vantage point of space is a revolutionary key to understanding the interactions between processes. Only from the vantage point of space can we make measurements nearly simultaneously of many different quantities on scales that span all the relevant scales of the system, because the Earth is a nonlinear system and all of the time scales and all of the space scales are connected. It is required to be able to make measurements of many quantities frequently at every place and for long, but over long periods of time with high spatial resolution and global coverage. And let me go back, if I can, on this, which I probably can't. Okay, there we go. And only from the vantage point of space, actually, can we make those sorts of measurements. NASA is presently flying, consider it to be 16 or 20 missions making measurements of many different quantities. Together, humanity, from the vantage point of space, is probably flying on the order of 100 to 150, probably closer to 150 Earth-observing satellite missions. They are providing key, not all, but key information for understanding our planet as an integrated system. And finally, let me point out, in this introduction finally, let me point out that since this happens to be the planet where all the people live, understanding our planet and monitoring our planet can then be used through predictions to positively influence the lives of every single inhabitant on Earth. You know, in NASA, we've got a bunch of different science divisions: heliophysics, planetary sciences, astrophysics, and each one, you know, has some particular claim to fame. Heliophysics says they have the star, and planetary physics says, you know, they got Saturn and all these neat planets, and astrophysics says by volume they've got us all. And I go, yeah, and we got all the voters. And we're not only making measurements from a disconnected set of individual missions, but actually at NASA and in all of the national space agencies, we're pushing observing system innovations. We're flying constellations of satellites to be able to have capabilities far greater than the individual, than the sum of the individual capabilities of individual spacecraft. We are developing approaches for flying particular spacecraft, which then characterize the relevant measurements of other missions which were launched for other reasons to allow us to get unified global measurements, and I'll show some of that. We're exploring small satellite constellations, both homogeneous and heterogeneous, and we're learning how to fly science instruments on commercial spacecraft, all of which are in service to understanding our Earth as an integrated system. And we've made many accomplishments over time. Susan talked about the biosphere and the global aspect of it. By making measurements globally with high resolution, stably, over long periods of time, we can actually see the grand complexity of the planet. I could spend 2 hours on this one. I won't. From the 30-meter resolution, 45-year Landsat data set, Hansen and his collaborators took 13 years of data and looked at changes in forest cover over the entire globe over 13 years at 30-meter resolution. We have that power and that opportunity and the processing to be able to do it, frankly, nowadays. An interesting part of this that I always like is this quadrant here is sort of a map of forestation and deforestation, gains and losses. And the purple in there is areas that both gained and lost forest. And you see the Southeast United States is probably the largest area in the world that happens. What's going on? Those are managed forests. 2% a year are being cut, so you have forest loss, and they're being replanted and you have forest gain. This all shows up in the satellite record. We know with accuracy and precision that sea level is rising in a global mean sense. We know that from satellite missions, primarily from NASA and Kinéis joint precision altimeter missions, making measurements that are accurate, or that are precise to 1 part in 10 to the 8th. But why is sea level rising? There are a couple of reasons, at least. You know, one of them, Susan would say, the shape of the ocean basin is changing. That can change sea level. That's on somewhat different time scales. We are taking water that was on land and putting it into the ocean by melting ice, but also by changing the temperature of the ocean, it expands and contracts. So from the altimeter measurements, we have a good idea, a precise idea of the change in sea level by gravity measurements, in particular from the GRACE mission. We can track the mass of the water in the ocean. And you can see that sea level on a global mean sense is rising at about 3 millimeters, 3.2 millimeters per year, plus or minus 0.4. But the amount of mass that we're putting into the ocean over that same period of time only accounts for about 1.8 millimeters per year of sea level rise. And therefore, we know that primarily the rest of it is the result of warming of the upper ocean, and that's completely consistent with the in situ measurements from Argo floats. So from the vantage point of space, we not only can see how the planet is evolving, but we can diagnose why it's evolving. We are measuring the changes in ice, both on land and in the ocean, from the vantage point of space. And you can see here that in the Arctic, which I, as an oceanographer, always had a problem with ice in the Arctic. I hated it when people could walk on my ocean. But we're taking care of that as a species right now. Not only is the extent of sea ice more or less relentlessly decreasing by about a factor of 2 over not too many decades, but you can see from the thumbnails here that our satellite measurements are also showing that the fraction of multi-year ice is decreasing. So you go from thick ice, which is primarily controlled by ocean processes, to thin first-year ice, which is primarily controlled by cloudiness, which changes the amount of solar insolation. It's these sorts of changes in controlling factors which can lead to climate tipping points and other rapid changes. We're measuring them from the vantage point of space. We're measuring atmospheric composition. You can see the Earth breathe from precision satellites that measure carbon dioxide concentrations in the atmosphere. You can see from the beginning of spring all the way through the major part of summer as the northern hemisphere land areas, the photosynthesis starts up, draws the carbon dioxide out of the atmosphere. A series of wonderful 5 papers in Science that was published towards the end of last year examined the complexity in carbon dioxide concentrations in the atmosphere in the context of El Nino. And different things are happening on different continents. We're making measurements from the vantage point of space of atmospheric composition to help policymakers. In particular, we have long-term measurements, precision measurements of stratospheric ozone concentrations. In part, the spaceborne measurements help to lead to the Montreal protocols, but the question that the policymakers have revolve in part around, are the protocols efficacious? Are they really changing the stratospheric ozone in the positive ways that they were intended? And shown here is the time series of satellite measurements of the size of the Antarctic ozone hole in the stratosphere. So large ozone holes means less stratospheric ozone. And the solid line here are the model predictions. And interestingly enough, and quite good, I think, is the fact that the model and the models and the observations are actually quite well aligned quantitatively. There's year-to-year variation, of course, but the Montreal protocols appear to be having their intended effect. Right now, we happen to be at the maximum, so sort of at the flat spot, but in the next several years, one would hope, if things continue to evolve as we predict that they will, that stratospheric ozone concentrations will increase rather rapidly. And by the 2070s or thereabouts, our grandkids or great-grandkids will be experiencing the same levels of stratospheric ozone as some of the elders of us did as we were growing up, when the dinosaurs roamed the earth. We are, as I mentioned, making heterogeneous constellations, using heterogeneous constellations, not necessarily making them. In this instance, characterizing and combining measurements from many, many different satellites in different orbits to, for the first time, understand precipitation globally. You can't measure precipitation in situ globally because most of the Earth is covered by water, and it's really hard to measure precipitation over water. But with the Global Precipitation Measurement Core Observatory and contributions from 10 other satellites, we now have on the order of a couple of hourly and a few tens of kilometer spatial resolution accurate measurements of precipitation over the entire globe. I like to say that before GPM, all we knew about precipitation is wherever I was going on holiday, that's where it was going to rain. We can measure soil moisture as well as precipitation, and see very interesting features. If you compare the soil moisture and sea surface salinity in the upper panel with the precipitation measurements in the lower panel, you could see interesting things like, hey, when it rains, soil moisture goes up. We did not have to, Susan probably knew that, but we don't have to have satellites for that. On the other hand, the soil moisture goes up, and then the Amazon floods and puts low salinity water into the western tropical Atlantic, and then there's all kinds of biological and ecosystem changes that happen there. So we're understanding connections between processes, and we're taking those measurements and understanding and turning them into focused information products for users and decision makers of all types. Obviously, weather prediction and extreme weather prediction is one way in which the view from space, one area in which the view from space has helped to revolutionize our initialization and assimilation of measurements into models. But even for the weather forecaster who is sitting at her desk doing forecasts, for instance, of and analyses of particular storms, hurricanes, tropical storms, extreme events, you can see that the satellite measurements are finding their way into those routine documentation of their analyses. Where for Hurricane Irma back in September of this past year, it says here particularly, a recent GMI, it's GPM microwave imager overpass, showed a 50 nautical mile wide outer eye wall with the inner eye wall weakening. So this was an eye wall replacement process. The satellite measurement was felt to be so key by the analyst to the analysis that they actually mentioned the mission by name. The same GRACE mission, the gravity measurement mission that we talked about, tracking mass of water in the ocean, is also used to look at subsurface water around the Earth. And we can see changes in aquifers on time scales of decades, whereas the natural filling time scales for aquifers can be centuries to millennia. The water that's being pumped out is being used for lots of good reasons, but nonetheless, we are changing our planet. And in the same way, GRACE and soil moisture measurements from satellite missions are being used in routine sort of county-wide resolution predictions and analyses of drought in the continental United States and elsewhere. The point that I'm making here just from these few examples is not only are we measuring, not only are we doing research to take those measurements to develop understanding, but we're turning that understanding into direct societal benefit through predictions. And this is an important point to get across to our funding stakeholders in legislatures and administrations. And finally, I'd like to end with a series of challenges which actually match in very interesting and fundamental ways those that the last two speakers have mentioned. The first one is a little bit different, but actually it goes back to Barbara, to something that Barbara intimated with her measuring systems. And that is, we tend as scientists to often be conservative. We don't like to think about it that way or ourselves that way. But there are technological improvements, which, especially in the arena of spaceborne measurements and observing system designs, which can potentially open the solution space with their own negatives and positives. And in my position, I work very hard to try and keep the solution space for future observing systems open and encourage system engineers to consider, but not to become seduced by, potential new technologies. It's really hard, especially when you're making $100 million or billion dollar or euro investments in observing systems, to do things different ways. And figuring out how to sustain new constellations, how to do the international governance of constellations of spaceborne measurements, where it's more than any single agency, more than any single nation can do, is really important. And we frankly are only developing the structures and the conversations that are necessary for long-term sustained measurements that way. Incorporating private sector information into the research endeavor, especially in the arena of space, where it used to be only the governments had sort of, the quantum of money necessary to get access to space. That's not the case anymore. Our commercial sector are making measurements of some quality. How to sort of mine the good stuff from those measurements in some rational way is something that, that neither the private sector knows how to do well, nor do our academic scientists understand how to do it. We in NASA are actually involved in initiating several pilots to try and look at this in different ways. And finally, we've heard from the previous speakers about data management, and I mean data management writ large, with so much data from so many diverse sources, all of which ought to be combinable. How do we keep high integrity and understand the pedigree, keep control over that? Free and open data exchange is obviously necessary to capitalize on the investment, and merely moving all that data around and understanding what's in it with visualization and data analysis tools are key. And with that, I know I've talked way too long, so I'll stop.
So before we begin our panel discussion, I'll open the floor for any quick questions for Mike. Yes, would you go up to the microphone, please, and introduce yourself.
Thanks for the very, is this working? Yeah. Thanks for the very nice talk. I'm Martin Kunz from the Max Planck Institute for Biogeochemistry in Jena. Here on your Outlook slide, you mentioned both incorporating the private sector more, and you mentioned free and open data exchange. Mm-hmm. And I think often these two don't go together very well. Can you comment on that potential conflict?
It's easy to hide behind that potential conflict, and it's true. But actually understanding what the cost sensitivity of various access to and distribution of data is really key, and we're trying to have those conversations. Much of the data, much of the analysis that we're doing as researchers does not require near real-time data. I would maintain that much of the economic business model of private sector Earth observation companies right now in space revolves around providing time-sensitive information to a variety of users, tailored in various ways. So it should not be a grand challenge, or at least an insurmountable challenge, for us to be able to have a discussion of value versus timeliness, latency, and value versus sub-distribution on certain time scales to come to an agreement with the private sector. If you take that sort of view, we might actually end up in a win-win situation. If you take the view that because there is not complete overlap in our objectives between the research side and the private sector side, then you're not going to have a conversation at all.
Thank you.
Okay, thank you very much, Mike. I'm going to turn the chair back to Jonathan.
No pun intended.
Yeah, or maybe there was. Well, look, if you're not an Earth observation scientist, I bet you really wish you are now, because what Mike presented was, I mean, you know, the results and what you can achieve with satellites really is pretty amazing. But actually, I mean, we've heard a wide range of different perspectives of what we've achieved in geosciences and some of the challenges going forward. And the idea of this part of the session now is to open it up to you, the audience, to really drill into some of the issues that were raised by any of the speakers, or all of the speakers. There were some common themes there. One of the common themes was data management, international coordination of programs, funding and data. So if you have a question, just come up to the mic and give us your name and we'll fire away. So, any questions to start with? If not, I think that's not a question, actually. I think that's something else going on there. Okay, yeah. Okay, all right. I'll chip in a bit. I'm itching.
Thank you, Chairman. I'm Koyan Wei from National Taiwan University. I think probably this is a proper occasion to ask the following. Because we are in EGU, AGU, and people like you just talk about transdisciplinary researches. But we know that each discipline, even subdiscipline, has its own kind of vocabulary, its ontology. So I'd like to hear, any one of you commenting on how do we do these transdisciplinary studies, researches, in terms of maybe funding, organization, and so on. Thank you.
Who wants to bite the bullet first on that? Any takers? Barbara? Okay.
So I think a very important aspect is to bring people together for extended times so that they can actually learn to understand the vocabulary of others. Not only the vocabulary, but also what is really known in the other disciplines and what are iffy or, a kind of hypothetical knowledge. And time is really important. And that is not so easy, of course, because everybody is very busy and, doing their own little corner of the research. But finding the right kind of framework to be able to spend a lot of time, to exchange and just, well, basically, yes, that's all I want to say.
Does anyone else want to comment on that? It's a very good question, actually, and it's one we battle with here at EGU because we have 22 divisions. A lot of people that come here will just look at what's going on in their own division and they won't even think about going beyond that. So
my comment was going to be more or less that on this meeting, this group of EGU meetings needs to find a way of bringing together the social sciences and industry. And we've been trying, I was president of this thing 10 years ago. We were trying 10 years ago to try and bring the industry here. We've failed, really. Now it's time to bring the social scientists in as well so we can solve some of these problems. But I don't know how you're going to do it. It really is a big challenge.
Yeah, I think it's a good point. I have a project where I work with people in statistics in my university, and really, it's like we're talking orthogonally a lot of the time. The terminology, the language, the way we see the problem is entirely different, and it's, even within my own university, it's a challenge.
So I'm going to suggest a partial solution, and the responsibility is partially yours. Earth system science and the cross-disciplinary nature of the problems is a relatively modern and recent observation. You are all engaged in that right now, and especially for those of you who are earlier in your careers, that's exactly what you should be doing, which is the science. But at some point in your careers, you might think about going over to the black side, like many of us have, and helping the field out by taking leadership positions even in governments and in the funding agencies. Then your knowledge of the essential cross-disciplinarity will become part of the policy of the funding agencies that you are helping to run. That will also help things, as opposed to simply talking to old people and trying to get them to change their religion.
Katrin, yeah?
Let me speak from the perspective of universities, as I represent an association of universities. I see that many of universities are setting now global challenges as strategies for their universities. So that means that you have to work in an interdisciplinary way within the institution. So once you set that strategy, it's up to the university to make it possible for researchers, not only researchers, but teachers to work in a interdisciplinary way. So it starts very early on, I think, at the first year of studying at universities, where we need to talk about knowledge accumulation, dissemination in a different way, do it in a different way. And so you need to create opportunities for researchers and teachers to do that. And then you also, especially in terms of research careers, reward that. And it's true not only in terms of sort of career promotion, but also in terms of funding decisions, that we don't always know how to reward interdisciplinarity well. So it's a question, I'm sure Jean-Pierre could talk about the panels, how they do interdisciplinary evaluations in an organization like the ERC. It's also a question about promoting researchers to the next level, hiring them and promoting them. And we actually wrote a paper on this. It has, I think, about 65 recommendations about what universities can do. I'm not going to go name all of them to you now. Come to me if you want the paper, I'll send it to you.
Okay, thanks for that. That discussion could obviously go on for quite a while, but I think I see some other hands. Nick, yeah, okay. Do you want to, go for it?
What we've been hearing about is interaction between Europe and the USA, mainly, AGU, EGU, which is excellent. But I would like to hear a little bit more about how this type of interaction should be extended on one hand to China, because China is already strong in this area and will inevitably become stronger. And on the other hand, the lesser developed countries, which might miss out. Any thoughts on that?
Yeah, that's a great question. I think, Katrin, you that was one of your bullet points, that it's key, actually, that we engage and involve developing countries in some of these grand challenges, particularly related to climate change, because it will affect them more than any other nation. But Jean-Pierre.
Well, it's evident to all of us that China is investing a lot of money and attracting a lot of people in science, in many different disciplines. I'm sure in yours. I know more the situation for mathematics because I'm a mathematician. I was the end of last week in a conference in the US, in Philadelphia, actually, and basically 2/3 of the young people were Chinese. That's the situation. So maybe one thing we should notice at the level of ERC, now we have a quite good collaboration with the NSFC, the National Science Foundation, Chinese National Science Foundation. And you may have heard one thing which We have to see whether it means a change or no change, but Deng Xiaoping creating the NSFC outside the ministry in a deliberate way to have really more agility to really organize things differently. And it was just decided very recently that NSFC will be absorbed by the so-called MOST, which is the Ministry for Science and Technology. So maybe this is insignificant and will not have no impact, or maybe it is significant. The leadership of NSFC has been completely changed. The new leaders are also extremely well-established scientists, so they are really people of great recognition, scientific community, so at least it shows the leadership is definitely competent scientists. But we have to see whether it changes or whether there's just well, some kind of administrative fix, but nothing more. But it's clear that China is moving forward and playing a more and more important role. And on top of that, is extremely ambitious in terms of its role in setting up facilities of world standing. So I'm sure you can comment on that with more details and content than I can. But this is very clear, and the level of ambition is extremely high.
Does anyone have anything to add on how we can be more inclusive and more engaging, in particular with developing countries?
Yeah, I just want to add one comment on developing countries, and that's in the UK there's quite a lot of money going to developing countries at the moment. The real challenge actually is how you evaluate that research. You know, it gets called research, but actually a lot of it is actually research/stroke development. And so what tends to happen is that it's very, if you're using the same metrics as you might use for your top quality university research in Europe, you cannot use that metric for some of the development stuff, at least initially. You know, it's a longer term trend in my mind.
I mean, yeah, it's a delicate balance between good intention and having sort of almost imperialistic intention, and yeah. Sue.
Well, I don't have an answer, but I feel like the big opportunity we have is now that you know, the internet allows people to take classes anywhere in the world. You know, a number of the students in our institute have been taking MOOCs to fill in things that we don't offer. And I feel like there needs to be more of an effort to make things available globally. I mean, that's part of open access, is that maybe you don't have to have as much money to get educated, but you have to have the basic access to the internet and you know, the language ability to understand what you see. And I feel like those, you know, those are things that are all happening. They're improving rapidly. Translation is becoming much better. So you know, some of these barriers may come down. Certainly, I meet every 6-year-old I know is a scientist, so, but we somehow don't get them all into the pipeline.
Maybe we should ask Mark Zuckerberg to help us out. He seems to be very good with moving data around. Or not. Chair's prerogative here, I'd just like to ask us a kind of follow-up question, which somewhat relates to the previous one, which is about how we can improve doing joined-up science. What I mean by that is I've seen numerous instances where there have been RC UK, that's Research Councils of the UK, funded initiatives that have parallel activities funded by, for example, NASA or possibly NSF or other agencies. And I think the space agencies do quite well in terms of coordinating their space segment, because, you know, if you're going to spend €1 billion on a satellite, you think quite hard about whether you need to do it or you cooperate over it. But I think at a national level, I see a lot of funding that takes place that is not very internationally coordinated. And if we really want to address some of these grand challenges, and they really are big problems, like we heard with, for example, extreme Earth, then we need much better international cooperation and collaboration and coordination of research. And we have people from the funding agencies, we have people from LIRA. I would like to hear a few thoughts about whether you think it's an issue and how we can improve on that.
Maybe I can start with even people who work outside of large programs. One of the points I had on one of my slides was, we do have a demographic shift where we have a lot of retiring scientists, which creates opportunities, but there are also the data that were collected by those people in a time when it wasn't possible to make it open access for everybody. And I think there's a chance of losing a lot of history. The Earth is the kind of place that you can't go back in time and remake a measurement. So, and there are efforts like, recovering lost data, all these things. But I feel like there's a tremendous curational challenge to taking, even if people put their data somewhere in an archive, being able to find it and synthesize it later. So I just wanted to throw that out as a challenge. Even outside of coordinated networks, you never, know what you're going to find. So.
Well, I can say something. I think you're right. If you look at the funding that's invested in Europe, for example, it's 80% or 90%, I'm not sure what number is the nations, and about 10-20% is Europe. So clearly the European effort is doing this interdisciplinary science. But we fail, for example, when you take oceanographic cruises and things like this, we fail to mobilize the Germans, the French, and the Greeks, or whoever, together behind big problems, right? Say the Southern Oceans, it's a big problem, and everyone's doing their own little thing, and we're not sharing ship time, we're not sharing personnel. So I don't know what process there is. There used to be a thing called Eurocores, which existed across Europe, which sort of did that a bit, but there is a wasted effort. I mean, there's examples of the Germans and the Brits doing exactly the same thing, pretty much on the same samples in the same site in methane hydrates, Yeah,
but we also talked about the Chinese research program. I mean, and how well coordinated is what we do in Europe and the US with Chinese research, for example. I mean, earlier on, Mike and I were talking about this at the coffee break, and I mean, I don't want to misquote you, but you felt that it wasn't so important that somebody was necessarily funded because they're at the end of an email or something like that, perhaps. But I'm not sure, or well, maybe I did misquote you, but I think it makes a big difference whether a researcher is funded to work on a project or whether they're just like a paper partner. Yeah, Mike?
Well, our conversation, just to set the record straight, at least on what I hoped I had said, was that it's not absolutely necessary that money, in my opinion, that money cross national boundaries, but rather the key in all of my experience and our international coordination group experience, the key is to articulate clearly the mutual benefit of the collaboration. It turns out that when everybody understands the mutual benefit, then we're all pretty persuasive people, and the governments and the institutions kind of snap into line. But if we can't articulate the same mutual benefits, then the difficulties grow sort of exponentially. So thinking really, really hard about why the collaboration is essential is a key to this.
We're rapidly closing, but I can take one more quick question if someone has a... Yeah, go on, go for it. Yeah.
Hello, thanks for the talks. I'm Mark Mallet. I'm a postdoc at CNES in France. but I'm Australian. And Australia is about to get a new space agency. Maybe you've heard of this. So in what ways, and this sort of follows on, in what ways can a new space agency make an impact on Earth observation? And what would the structure of that space agency be?
Wow, okay.
Tell me your secrets.
In the interest of people going to lunch, I won't answer it in detail.
I think that's a great question for us all to ponder over lunch, actually. I mean, thanks for the question. I think we are pretty much out of time, and there is, hopefully, there is a medal lecture in here in 15 minutes' time, so we really do need to wrap up. I would really, really like to thank our list of 6 speakers to rising to what was, in effect, an impossible challenge and putting out some really interesting ideas and some grand challenges and a lot of thoughts for us to take away for the rest of the week. So please show your appreciation to all of them. And I'd just like to say at the very end that you can see a slide up here which shows that we've launched a questionnaire on geoscience funding in Horizon 2020. So if you've had some, particularly if you haven't had any, maybe you'd like to fill in the questionnaire and it takes 10 to 15 minutes and it will be very useful for us to feed into the Commission for planning for FP9. And enjoy the rest of the week. All of you, thanks ever so much.